I wanted to make a video showing how I made this neat volume rendering thing in Unity. A lot of people on Twitter have been asking me about it, so all the code for this entire scene will be in GitHub. You can find that in the description. But basically what it is a really simple, really standard Raymarching shader that just takes a volume texture and we march through it. We calculate accurate light based on the lighting position. And I found that a lot of the videos on Raymarching were difficult for me to follow personally, just because they're very technical and I found sometimes skipped over some of the parts that might seem obvious to some people but weren't obvious to me. So this is just going to be a really simple explanation, walkthrough of how I made this, step by step. I'm going to show everything, try and explain everything the best that I can. Might be a little long-winded. I'm not terribly great at making tutorials. I'm probably going to stumble through this pretty hard, but at the end we're going to get something like this, which looks really cool, I think. We're going to briefly talk about how to generate volume textures in Houdini and import them into Unity so we can use them in our shader. And we can, show different volumes and stuff. There's a lot of other tricks you can do to make this run faster, but I'm not going to include those because I feel like they overcomplicate how this works, and I just want to explain it really simply. I'll include some links in the description that are some really good resources for that kind of stuff. Or maybe I'll make another video too that expands on this further if people are interested. Without further ado, let's make cloudy things. And yeah, so I have Unity open. It's one of the latest versions, URP installed. I think it's URP 12, and just a simple scene here. We're going to be using Amplify Shader Editor, just because that's what I'm familiar with. Most of the raymarching happens in a custom expression, custom shader code anyways. So we're going to put together a volume renderer of a sphere to start. And then we're going to jump into Houdini to generate a 3D cloud texture, like a density volume. I'm going to be using Houdini just, again, because that's what I'm familiar with. I'm sure you can do this in Blender or whatever. But in Houdini, it's like a minute. Super easy, super fast. I'm going to try and do this video in one take, but I'm probably going to stumble a lot and make a few mistakes, but that's okay. So we're just going to make a unlit shader, and we're going to call this Raymarch, and it opens up the Amplify canvas. Actually, we're going to reorganize our screen a little bit because I like to put my inspector over here, and I like to put my project window down here, and I like to put this like this. This is how I like to do it, but I'm going to maximize this anyways. Okay, and now we have our shader. We're going to create a material from it, and we're going to stick it on a cube. So just normal cube. Really quick example of raymarching and how it works before we start is, so we're going to have our cube, which we're going to represent by box, and then we're going to have our camera position, and we're going to have a direction in which the camera is looking. And we're going to basically, for every pixel that this camera can see on this box, we're going to find where the ray intersects, and then we're going to shoot it through this box like this, right? And then for another ray, we're going to shoot it through like this, and we're going to step through this box in small increments. So we're going to start here, and we're going to step forward a little bit, we're going to step forward a little bit, we're going to step forward a little bit. And at every one of these points, we're going to sample this the texture that's inside this volume, or the density that's inside this volume. And we're going to see how much stuff is right here, and we're going to add it all up and kind of accumulate the density as we go through. And that's how we get like the total volumetric density. And then later we're going to light it. So it reacts with light. So say we have our big old sun right here. That needs a nice color. For every pixel then that we're sampling the density for, we're also going to figure out how much light reaches this. So like for this pixel here, we're gonna step forward, and at every step we're gonna also cast a ray from the current pixel we're at towards the light, and then we're gonna step through here and accumulate how much light would reach this pixel. So it might sound a little complicated, but it's really just getting the ray, finding the spot we're starting at, and stepping through. And every step, we grab the density, and we just kind of accumulate it, add it together, and then at the very end we do some math on it to figure out how much light would be like transmitted through the object, to kind of make it a little more physically accurate. Yeah, so let's jump back into Unity. Let's start by just making a custom expression, and we're going to call this Raymarch. Ooh, is this code going to be too small to see? It might. I'll do some zooming in on the screen here so you guys can see. So we know that we need a float 3 for the array origin, which is often sometimes written as just RO, but array origin. And then we need a array direction, which is also a vector 3, and this is the direction the ray is pointing in. And then we need a, let's just use an int for num steps, for how many steps we're going to take through the volume. So we have num steps and we have step size. So num steps and step size is just like how many times we're going to do each step, num steps, and then step size is how far we should travel along the ray for each step. And yeah, so like we could calculate for the ray. We could say that, okay, this is the position the box enters, this is the position the box ends. Say we want 16 steps between there. We could just take this distance and figure out how long each step should be in order to fit 16 steps. We're not going to do that. We're not going to do that. We're just going to start here, and we're going to give it some arbitrary distance that looks right, and some number of steps that looks smooth. But this is one optimization you could do if you're doing volume rendering inside of boxes only. But to keep it simple, we're not going to do that. So, so we need num steps. We're just going to make some shader properties for this. Step size. We're going to have to fiddle with this to figure out what looks right. And then we're just going to stick in the output color for now. So we need the ray origin, and that's where the ray starts from. And in a full volumetric like world, I guess, you would start from the camera position, right? And then you'd start stepping through here. But we know that we're not going to be rendering anything before we get into the volume. So we can actually just make the ray origin the world position of the box, which is easy. So world position, and we just plug that in. For the ray direction, we can take the world position and we can subtract it from the camera position to get this vector. and then normalize it, which is also very easy. So we just take world space camera position, and we go subtract. Is that backwards? This might be backwards, but if it's backwards, we can just adjust the step size to a negative number if we really want. To start, we're just going to Raymarch through a sphere. So I guess let's make it so we can move around the sphere just for fun. Vector 4, so we're going to have x, y, z position and the radius of the sphere is what we're going to use those numbers for. And we're going to have to do a little bit of like ray intersection math. And we're going to say everywhere inside the sphere has a constant density of, say, like 0.1 or something. And then outside the sphere has no density. But okay, so let's write our loop. So we're going to have a float density, which is going to be our final density that we get out. And that's all we need there. And then we're going to make a for loop. Int I equals 0, I is less than num steps. And that iterates through the number of steps. We're going to take array origin, and we're going to step forward. So we're going to start at wherever we are right now, and we're going to move forward the distance of step size in the direction of ray direction. And so we go ray origin plus equal to ray direction times step size, right? So that's easy. Now we have the new position that we want to sample the volume at. So let's just go get sphere density. After we're going to actually replace this with a texture lookup that we're going to generate in Houdini, like I said. And that's actually a little bit easier to do, but it requires going into a different program. So I want to skip that for just a moment. So get the sphere density. So we have the ray position, and we can tell if the ray position is inside the sphere by seeing if the distance from the ray position to the sphere center is less than the radius of the sphere, right? So if we go so let's just get the length first. So distance, sphere distance is equal to the distance from ray origin and sphere.xyz. And then if sphere distance is less than sphere.w, which was our sphere radius, we are inside the sphere. And if it's bigger than that, we are outside the sphere. We're currently sampling inside or outside the sphere. And if we're inside the sphere, then we know that we want to grab the density of the inside of the sphere, and we want to accumulate it. So if we're inside the sphere, density is plus equal to some small number, 0.01. And then should that be it? And we can return density. Now we have let's make another variable on here that's just density scale, just so we can play with the density outside. And then we also want to density scale. We missed a less than sign there. We are spelling things wrong. There we go. Okay, so we start at the ray origin. We step forward in the ray direction, the length of step size. We calculate the density at the new position we're at. And if we're inside the sphere, we add to the density. And then we return density. Now, there's a transmission formula that determines kind of how light works a little bit better in the real world. It's like the basically we just go exp minus density, and that it changes it from a linear accumulation, I guess, into an exponential one or something. Anyways, so yeah, now we have our simple Raymarch. Okay, so we look at our cube. We need steps to be an actual number, so let's turn this up to 64. Step size might need to be adjusted. Our sphere is at 0, 0, 0, but it needs a radius of something. And our cube should be at 0, 0, 0 for now, too. Hey, so we see something going on here. Let's adjust our step size. And let's make our radius a little bit smaller. There we go. So we have our first volumetric rendered sphere. And we can move it around. And we can move it back and forward in space. Change the radius. Cool, cool, cool. Okay, so now that we have this really simple thing working, we're going to jump into Houdini and change this so that we step through a volume texture instead. And so we have Houdini opened up, and we're just going to put down a box. And we're going to also put down a point light. Just so we can see what's going on here. And then inside of our box, we are going to use the... Actually, we're going to get rid of this. Just use a sphere. And then we can use the cloud node, which will take the sphere, and will turn into a cloudy-like thing. And then we can use the cloud noise node on top of that, and it makes it all puffy and cool. And then we use the labs volume texture export node, which will slice this up into a texture that we can then import into Unity. So it's really easy. I'm going to change the up axis to Y because that's what Unity uses. And I'll just call this cloud volume 1. We're going to save it as an EXR. And we're going to hit render. So now we have this cloud volume texture. Houdini watermark. I'm using the free version of Houdini, so we can't export this out to a really large file, and there's this watermark, but you can just go into Photoshop and erase that if you really want. So in order to change this like sliced texture to 3D texture, we just change this to 3D, and we enter in the right number of rows and columns. It's 8 by 8. We're going to uncheck sRGB because this is density, not color. And then wrap mode can stay on clamp, and we hit apply. And now we have this cool cloudy texture. Ooh, cool. And while we're over in Houdini, we're also going to export out, what do we want? Rubber toy, maybe? We can take this cool rubber toy default geometry and plug this into the cloud instead of the sphere. And now we have a cloudy rubber toy, which we're also going to export out to, and just name it Cloud Volume 2. And maybe we can make it a little bit more like noisy. And still it's like the general shape of the rubber toy. Okay, we render this, and now we have that. So back to Unity. We change this as well to 3D 8x8. And now we have cloudy rubber toy. See, I'm going to take these into Photoshop. I'm going to take these into Photoshop and really quickly remove the watermarks just by erasing them. Okay, so we got rid of those Houdini watermarks. So there's our volume. So if we go back to our Raymarch material, now instead of doing this, are we inside of the sphere check, we can just sample our 3D texture at the ray origin and get the density from there. So float sampled density is equal to text 3D of our volume, and then array or so we sample our volume at our array origin, so world position, and then we just return the art channel of the volume because that's all we're really caring about. So we need to add our volume sample here, sampler 3D volume, and then we add a texture object node, name this volume, and autocast it to locked to texture 3D, so we'll only accept a 3D texture and plug that in there. And then back in our Raymarch code, we just want to accumulate the density like we were before. But now we're just going to use our sampled density and multiply this by our density scale. So if we save this, and we go back to this, and we add in our cloudy volume, we have something. Just going to get rid of this sphere input since we don't need it anymore. So yeah, we have a volume now. A few problems is that it doesn't move with our object since it's being sampled in world space. And it is starting the sample from the top right corner. So let's make a new property that's called just offset, and make a new variable, plop it into the Raymarch node, and instead of sampling it at just the ray origin, we're going to sample at the ray origin plus the offset. And now if we move this around, we can offset it. So like since it's 3D texture, it should be offset by 0.5 in every direction to center it. And if we play with the density scale a little bit, yeah, we have a cloudy thing. And we change it to the rubber toy. And now we have a rubber toy density. So that's great, but it's not reacting to lighting yet. So we will do that next. But first, this isn't moving with the object. And I think I would like it to, right? So if we just take our offset and maybe add the object's position to it, would that work? So we go object to world, and this will get the world space position of just like the object center. And it's backwards. So we need to subtract. Yeah, cool. Cool. Okay, so now we're going to do lighting. And just a quick refresh. Lighting, we're going to get the light position, and we're going to get the direction from the current sampling position, the current ray position that we're checking the density at, and we're going to draw light ray from there to the sun, and we're going to step through and accumulate how much light we've received. And then we're going to do a little bit of math on that and make it look nice. Again, I don't know if it's the best way to do it or physically accurate, but that's okay. So we need a light steps, and this is going to be int, and it's going to be how many steps we're going to make when we're marching the light, and then we're going to have light steps size, which is how large each step is going to be. And we just want to control these shader properties so we can find what looks nice. Num light steps and light step size. Fix that. Okay, so now I wish I could maximize my scene a little bit nicer to still show this volume, but have most of the screen over here. Okay, so we still need the density. We're going to actually make a new float that's called transmission. And so we're going to initialize these to 0. And transmission is just like how much light or how much visibility is transmitted through the density. And that is actually just what we're doing here at the end. Transmission is equal to exp minus density. So, okay, now for our light, we have the density at this position multiplied by the density scale. We have a ray origin plus offset. So we're just going to actually make a new float 3 and just take this. Oops. So we're just going to make a new float 3 and call this sampling position, and that's just going to be this, just because we're going to use this position in the Lightmarch 2. So we sample the position, that's good. So now after we grab the density, we can go and start our Lightmarch. So float 3, we're going to have a light ray origin, and that's going to be sample pose, and then we're going to have a float 3 light direction, and so light direction is just the direction to the light, so we can get this just by passing it in, light dir, and then world space light direction. And this will be the light direction for the main directional light. We don't need this. We can just, we already have one called light dir. We don't need to make another local variable for that. Now we're going to do our light loop. So for j equals 0, j is less than light steps, light, j is less than num light steps, j plus plus. Light loop. We're going to do the same thing that we were doing up here. So we're going to take the light array origin, and we're going to add to it the light dir times the light direction times by the light step size. And then we're going to sample the density texture at this new position 2. So float light density is equal to the same thing that we're doing here. Text to D, volume, and light ray origin. Then just the R channel of that. And let's create another photo up here that's just called light accumulation. And this is just the density that we're accumulating with every step here. So light accumulation is plus equal to light density times density scale, like we were doing before. And that's kind of everything we need for the Raymarched loop. What if we just return that and see what it looks like? Did I spell that right? No, we got some errors. Because we used a different name there. I'm sure if you're watching this video, you're going to pick out all these errors, these missed typos as I'm going through it. J is less than num steps. What's going on here? For j, int j equals 0. We stick this right here. So num light steps, just put that at 16, and now we have some sort of lighting thing happening. Doesn't really look like lighting, but we do have something happening. we're actually going to change the output type here to a float 3. And instead of just returning the light accumulation, we're going to return a float 3 where the first one is the light, and the second one is the transmission, and the third one is just 0 for now. And then if we go over here and we can split this, we can see the lighting in Y and the density in, or the lighting in X and the density in Y. Okay, so we're almost there now. So that doesn't really look like lighting just yet. It's weird and all white. Like changing the density scale doesn't really do much here. Where's our light step size? Changing our light step size doesn't really do much either. If we increase the step size, we can see that it's like getting around the edges. It is changing a little bit, but it doesn't look like lighting. So that's the last thing that we have to do. And this is kind of the most complicated bit I found. I don't really understand what exactly these equations do, but two more variables in this. We need a float that is going to be called light absorb. And this is how much of the light gets absorbed into the volume as we do the light march. And then we're going to have another one that's called darkness threshold. And a lot of these equations are actually just coming by from this video. And this is a great video if you haven't seen it already. It explains stuff really, really well. But I wanted to kind of put together a full tutorial of how to do it from start to finish. But yeah, Sebastian makes really, really good videos, really good interesting stuff, so you should go watch it, absolutely. But the lighting calculations that we're going to do now are basically pulled straight from this video. And he explains what they're doing a little bit better and how they work. But okay, so we have a light absorb and we have darkness threshold. So light absorb and darkness threshold. I always spell threshold wrong. We just plug these in. And now we have to do a little bit of changing around of how this works. So first of all, let's just make a float that's called final light and equal to 0. So we accumulate the light at every step, and we want to change that to I'm going to run this through this transmission equation. So we can go light transmission is equal to exp of minus light accumulation float shadow. And this is just going to be darkness threshold plus the light transmission times by 1 minus darkness threshold. And what this does is it lets you change where the shadows begin, kind of, I guess. And then we figure out the final lighting, which is just final lighting, or final light, plus is equal to the density from up here. And then we multiply it by the transmission image. Or sorry, so it's density from up here. And then we multiply it by, actually we need another value here. That's called transmittance. Let's just default as 1. Transmittance. That's how much light is going to be transmitted versus how much light is going to be absorbed, right? So density times transmittance, and then times by our shadow. And then transmittance, we multiply it by exp minus density times light absorb. So then we can change this to our final light. Transmission is like the density accumulation, which is right there, but we then want a transmittance as well. And does this compile? No, it does not compile. What are we missing? Redefinition of, is that why? Float transmittance. Oh, it's because we have 2 transmittances. And what's the problem here? Unexpected token. We're missing a bracket right here. Oops. Okay, so I realized that when I set up this project, I accidentally clicked the wrong template and set it up as a 2D project. So I just changed this over to an actual URP 3D project. And now the world space light, it just works as you'd expect. So rotate it around. We get really cool lighting on this volume. Yeah, okay, so now that that's all fine and dandy, so we have X as our lighting. We also have this Y value, which is our density. And we can kind of just throw that straight at the opacity, really. And if we change this to a transparent shader, oops, actually we have to 1 minus it. Does that work? Cool. Now we have like this volume cloud. Now there is a little bit of weird glitching on the sides, and there's this stretching. I know that stretching is from our 3D texture having a value right at the end, since this is set to clamp. Ideally, you'd want like a little bit of padding around the edges of your volume. But yeah, now we have this cool looking cloud that reacts to light. We can do some fun stuff with taking a lerp between two colors. I like to set them to HDR just for fun because we want to make them like over bright. So yeah, if we lerp this between two colors now, we can make the shadow like whatever we want artistically. And again, we can change how much light gets absorbed. Lots or little. We can change the darkness threshold. If we do that though, we should probably saturate this before it goes into the lerp. Kind of get like a really soft shadow there. Transmittance is, again, how much light gets through. And you just have to kind of fidget with these numbers until you find the right values. It's like we can increase the number of step sizes, but then we'd want to decrease the step at, or the distance at each step. Then it does start to slow down pretty drastically. So it could keep the number of light steps down as low as you can and still get nice results from it. Because again, right, it's a nested loop, so 8 iterations times 64 iterations for every pixel. It's doing a lot. Yeah, so we can drop in our other volume here too, and now we have our cloudy little rubber toy. And one cool thing about this, actually, the way that we're doing the Raymarching, let's go back to Houdini for a second. And we'll make something that has a really obvious, like, overhang. So let's just make a box. There's our cloudy box. And then let's shrink it down a little bit and move it down. And then let's get a torus, I guess. And we will boolean these two together. Union. So we have two of them, and then we're just going to make this smaller. And come on. I want to make you thin and this should hopefully be all right. We'll see. Anyways, we'll export this to Cloud Volume 3. And then we'll change this again to this. And if we plug this in here, oops, just a clamp, just so we get one of them. So the really cool thing about this is that you can see that it's actually casting shadows from this cloud onto this cloud below, and it's just a result of the way this light march works is because then, like for this pixel right here that's in shadow, it's marching towards the light above it, and it says, okay, there's no density, there's no density, there's no density. Oh, but now there's density, so I should be getting shadow, which is really nice, easy consequence for that. Yeah, you can see the stretching really bad here now, and that's, again, just because there's no padding on this. The outside of this cube should be all black, but yeah, that's pretty cool. You can change the colors. You could even like take this lighting term that we have over here and do a like scale offset and maybe also a power, I guess. Throw saturate between both of these because why not? And just go like lighting, the scale offset power, 1, 1, scale offset power. So now we can like just kind of adjust the lighting however we want. Want to make the shadows more prominent or less prominent, or sharpen where the lighting is, multiply it up to get something like more stylized. We could even posturize. We could even posturize this based on some property to get like a banding effect, which looks kind of neat, stylized. So yeah. Wow, wow, wow. Cool. Okay, that's it. Hopefully I didn't miss anything.